Welcome to AI Paper Slop. Today we are jumping straight into a paper called Thinking in Blender.
Right, that's staged executable inverse graphics with vision language models from a team of researchers at Cornell University.
Exactly. And let's just give you this 60-second core insight right out of the gate. This paper proves that a standard pre-trained vision language model, specifically Claude Opus 4.7, can do executable inverse graphics from just a single 2D image.
Yeah, and the crazy part is it completely bypasses specialized 3D foundation models.
Right. It ignores multi-view supervision entirely.
Which is huge. Instead, the system just acts as an autonomous agent writing fully executable Blender Python code.
Literally just writing scripts to recreate that 2D image as a complete, fully editable 3D scene.
And, the real breakthrough here comes from abandoning this idea of monolithic code generation.
Yes. Instead, it mimics the staged, iterative workflow of a real human 3D artist.
So it goes from scaffolding to geometry, then materials, composition, and finally lighting.
And you end up with a parameterized 3D scene that is perfectly ready for novel view synthesis, editing, and even physics simulations.
I mean, the broader implications here for the whole machine learning space are just staggering.
Oh, absolutely.
We're looking at this hard pivot from implicit neural representations of 3D space, which have, dominated the last few years.
Yeah, like NeRFs and stuff.
Right, moving back from those to explicit symbolic editable code, and it's being generated entirely by a general purpose model just operating straight out of the box.
Well, to really anchor this, I think we need to define why inverse graphics is such a notoriously under-constrained mathematical nightmare in the first place.
It really is a nightmare.
Because when we take a 3D world and compress it into a single 2D image, we force this massive amount of data loss through the projection matrix, right? The z-axis, the depth, is just instantly flattened.
Completely lost. And beyond just the depth, the distinction between a surface's inherent color, its albedo, and the shadow cast upon it becomes totally ambiguous.
Yeah, like a dark patch of pixels on an image. It could be a black texture, or it could just be a brightly colored surface sitting in a really deep shadow.
Exactly. And that ambiguity is the major bottleneck. The inverse problem is basically attempting to look at that flat array of pixels and mathematically reverse engineer the original 3D geometry.
Which is so hard.
Plus the precise material roughness, the specular values, and the exact position and intensity of all the light sources.
And traditionally, trying to solve that requires some really heavy external constraints.
Yeah, you either need large-scale multi-view supervision, so feeding the system dozens of photos of the exact same object from different angles to triangulate the depth, or you have to rely on these complex differentiable rendering pipelines.
Right, and differentiable rendering is essentially trying to turn rendering into this two-way street.
Exactly.
Instead of just taking 3D shapes and lighting to calculate the pixels on a screen, it calculates all the math backward.
It looks at the difference between a rendered pixel and the target image, calculates the gradients, and updates the underlying 3D parameters to try and inch closer to the goal.
But even that requires a really solid initialization, or it just gets trapped in local minima. So recently, the field has just been, throwing massive foundation models at the problem.
Right, training highly specialized models on huge 3D data sets just to guess the missing depth.
But wait, the fundamental shift in this paper is stripping away those specialized 3D data sets, which makes me wonder, and I'm sure you listening are thinking this too, why do we want a Blender program in the first place?
That's the million-dollar question.
Because we've seen this explosion of image-to-3D models lately, NeRFs, 3D Gaussian splatting. They already give us this incredible visual fidelity from single images.
You do, but the key difference really just comes down to editability and control.
Exactly. Generating a NeRF is kind of like being handed a beautifully baked cake.
I love this analogy.
You can walk around the cake, you can photograph it from different angles, but the structure is totally baked in. If you look at it and realize, I actually wanted a chocolate cake instead of vanilla.
You can't just swap out the flour and add cocoa powder?
No, you have to bake an entirely new cake from scratch. But executable inverse graphics gives you the exact recipe and the raw ingredients.
It gives you the human-readable Python script.
Exactly. If you want to change a parameter, you just tweak a single variable in the script.
Because that distinction between a neural representation and a symbolic representation completely dictates the utility of your output. A neural model encodes a scene inside this black box neural network.
You can't isolate the lighting from the texture.
You really can't. But by forcing the VLM to write a Blender script, we force semantic disentanglement. The model has to explicitly define the XYZ coordinates of a point light.
Right.
It has to explicitly declare the Boolean operations used to carve out a window or assign a numerical value to a shader for subsurface scatter.
Which is amazing, but it introduces a massive context window problem. We want the code, sure, but asking a VLM to hold all the spatial coordinates, lighting math, material physics, and object hierarchies in its head all at once.
Yeah, and output hundreds of lines of perfect Python code zero shot.
It's a guaranteed recipe for hallucination. It will just output total spaghetti code. The syntax might technically be perfect, but the scene will render as this chaotic mess of intersecting polygons.
And that failure of monolithic generation is exactly what forces the paper's main architectural solution.
Right, the SEIG framework, staged executable inverse graphics.
The researchers decompose the task to basically bypass the model's cognitive overload. It mimics a human production pipeline.
Because you wouldn't expect a junior 3D artist to deliver a perfectly textured, ray-traced final render on their very first pass.
Not unless there's some kind of prodigy. You break the task down into manageable milestones.
So SEIG starts by initializing a really coarse scene scaffold. It writes the code for simple geometric primitives, just dropping cubes, spheres, and cylinders into the virtual space.
Just to lock down the approximate object layouts and the overall proportions.
Yeah, and once that crude blockout is set, it moves sequentially. It tackles the geometry first, refining those simple primitives into complex shapes using modifiers.
Then it moves on to writing the material logic, defining all the colors and textures.
Then object composition, so making sure objects are actually resting on surfaces properly instead of just floating in midair or clipping through the floor.
And then finally, it dials in the lighting environment.
But the sequence is just part of it. The framework would still drift into hallucination without the agentic Generator-Verifier loop running at every single stage.
Oh, the verifier is crucial. The VLM generates a chunk of code for, let's say, the geometry step.
Okay.
A separate verifier module takes that script, actually executes it in a headless instance of Blender, renders an image of the current 3D state, and then feeds that render directly back to the VLM alongside the original target image.
So it's basically operating like a blindfolded sculptor. The VLM writes the code in the dark, but this verifier loop allows it to take the blindfold off for a few seconds.
That's exactly what it's doing.
The model looks at its own rendered output, compares it to the target photo, and engages its multimodal reasoning. It actually calculates the visual discrepancies in pixel space.
It'll realize, oh, the specular highlight on this surface is way too sharp, or that cylinder is a bit too wide.
Right, and then it translates that visual error into symbolic parameter adjustments. It puts the blindfold back on and rewrites that specific line of Python code controlling the radius.
And isolating that feedback loop to one specific factor at a time is how it maintains its stability. When it's refining materials, it's purely focused on the difference in color and texture.
It totally ignores the fact that the lighting isn't perfect yet.
Right, it methodically steps toward the final reconstruction without getting completely overwhelmed by all those interconnected variables.
And to really gauge the significance of this, we have to look at the experimental setup. Because the researchers used Claude Opus 4.7 for both the generator and the verifier modules.
Yeah, and they used it entirely out of the box.
Which is wild. No fine-tuning on 3D assets, no specialized prompt tuning, no task-specific supervision at all.
It's just raw Opus 4.7 interacting with the standard Blender API.
So how did it do against the baselines?
Well, they pitted SEIG against the closest existing framework, which is VGA Vision as Inverse Graphics Agent. And VGA was evaluated in two drastically different configurations.
Okay, what's the first one?
The first is VIG Full, which utilizes this massive specialized toolchain to try and give the language model a head start. It incorporates SAM, Meta's Segment Anything model, to pre-calculate pixel masks for every distinct object in the 2D image.
So it's doing all the heavy lifting up front.
Right. And then it uses SAM 3D to lift those 2D masks into initial 3D point clouds and meshes, all before the VLM even begins its write, render, revise loop.
So it's arming the pipeline with really heavy task-specific artillery. SAM and SAM3D are specifically trained to parse depth and object boundaries from flat images.
Exactly. VGA Full basically hands the VLM a pre-constructed 3D puzzle and just asks it to refine the pieces.
And the second configuration?
That's VIGA VLM only. It strips all of those specialist tools away. It removes SAM and SAM3D entirely,
forcing the naked VLM to attempt the entire monolithic code generation and revision loop on its own.
Exactly. And the performance metrics here reveal a massive takeaway for anyone in AI research. SEIG, using only the out-of-the-box VLM, vastly outperforms the purely VLM version of VHA.
Which we expect, right? Because we know monolithic generation just collapses under its own weight.
True, but SEIG also decisively beats VAA full, the version that was armed with state-of-the-art specialist segmentation and 3D reconstruction tools.
Wait, a naked language model beat a pipeline loaded with highly specialized computer vision tools?
It did.
That seems so counterintuitive, but I guess it exposes the inherent flaw of hard-coding geometric assumptions early in a pipeline.
That's exactly the issue. When VGA full uses SAM 3D, it forces a very specific interpretation of the 3D space based solely on a single 2D image.
Right, so if SAM 3D hallucinates the depth of an object, or maybe misinterprets a shadow as a physical edge, it passes that flawed geometry down the entire chain.
And the VLM just gets boxed in. It's forced to write code to patch and texturize a fundamentally broken mesh. It wastes its entire context window trying to fix the errors of the specialist tool,
Rather than just building the scene logically from the ground up. So SEIG really proves that harness design, the way we structure the task decomposition and those feedback loops, is far more critical than just plugging in external specialist models.
Absolutely. By allowing the VLM to organically iterate from a blank slate, the framework taps into these incredibly rich latent priors about 3D structure and lighting physics and spatial relationships.
Which are already embedded in the weights of general-purpose language models.
Right. We don't need to glue a disjointed toolchain together to teach a VLM about 3D space. The model already absorbed the logic of physical space during its massive pre-training on human text, code, and imagery.
We just needed a staged human mimicking loop to actually extract it.
And the visual fidelity demonstrated in the paper source material totally validates this. The paper provides several complex reconstructions, and the detail achieved purely through symbolic code generation is pretty remarkable.
Yeah, I was looking at the dessert scene they included, and it is a perfect example of this complexity.
It's a great example.
The target is just a single 2D reference image of a blue 3D ice cream swirl, kind of resembling soft serve, and it's sitting inside a square dark brown box.
And the composition is really dense. There's a square waffle leaning against the ice cream.
Yeah, and an intricately textured Oreo cookie, a striped wafer stick protruding from the top, and some strawberries resting at the base.
And the SEIG reconstruction doesn't just output a single fused blue mesh. It writes the explicit Python code to instantiate individual geometric primitives and apply targeted deformations to each one.
Oh, wow.
It actually writes the material nodes to differentiate the matte, porous roughness of the waffle from the high specular glossy finish of the soft serve.
And it mathematically positions that wafer stick to intersect the ice cream at the exact precise angle observed in the reference image.
It's wild. There's also this architectural scene they show. It features a stylized, low-poly white church with a green roof and a tall steeple.
Oh, right. And the building sits on a terrain dotted with these round, stylized trees and scattered rocks.
Yeah, and what the Blender code reveals here is a perfect understanding of spatial hierarchy.
What do you mean?
The VLM writes the code, recognizing that the steeple is actually parented to the roof. And the trees are instantiated across the surface of the terrain, while the rocks are distributed procedurally at the base.
So it understands how the objects relate to each other structurally. And that underlying scene graph is where the true value of executable inverse graphics is realized.
Because the output is a highly structured hierarchical Blender file. The downstream capabilities far exceed anything you can do with a NeRF or point cloud.
Exactly. You are no longer bound to the single perspective of that original 2D image. You can move the digital camera anywhere in the scene.
Right, if you want a close-up of the back of the ice cream swirl, you just reposition the camera in Blender and hit render.
And the math calculates the hidden geometry perfectly because the VLM built the entire object, not just the face that was visible in the photo.
And you can perfectly relight the scene too. Just grab the simulated sun in the Blender viewport and drag it across the sky.
The cast shadows from the church steeple will accurately stretch and distort across the terrain. It's calculating real-time bounces and ambient occlusion.
And beyond just novel views and lighting, you unlock granular semantic editability. Modifying the scene is literally as simple as tweaking a variable or deleting a line of code.
You can just open the outliner in Blender, select the waffle object, and hit delete. The waffle vanishes, but the rest of the scene remains entirely unaffected.
Or you can select the base of the dessert, jump into the shader editor, and completely change its properties to turn it into a donut with sprinkles.
The model didn't just capture a superficial 2D pattern, It captured the underlying logic and the object independence of the scene.
And because it's a native Blender environment, it means the geometry actually has volume and physical properties.
Which means physics simulations.
Exactly. You could immediately apply physics to the generated code. You could run a fluid dynamics simulation over the church model just to see how rain interacts with the slope of the roof.
Or you could assign rigid body physics to the dessert scene. Imagine dropping a digital bowling ball onto the soft serve and watching the physics engine calculate exactly how the waffle, the Oreo, and the strawberries would shatter and scatter across the floor.
All based on their mass and collision boundaries. If you tried to apply a physics simulation to a NeRF, you would just get a smeared, blurry distortion of pixels.
It wouldn't work at all. So the paper really solidifies this critical thesis. Executable inverse graphics is totally achievable using standard pre-trained VLMs without relying on specialized 3D datasets.
By breaking the problem down into a staged loop scaffolding, geometry, materials, composition, and lighting, we allow the model to use its multimodal reasoning to bridge the gap between 2D pixels and explicit 3D geometry.
And the downstream implications of this bridge push us in some really provocative territory, especially regarding the sim-to-real gap in robotics.
Oh, absolutely. Right now, we spend immense resources having human engineers and 3D artists build bespoke simulation environments for robots to train in.
But if an out-of-the-box VLM has the latent physics and geometry priors necessary to write perfect Blender code from a single image, well, we are looking at the foundational step toward autonomous simulation generation.
It creates a pathway where a machine can rapidly internalize and recreate its own environment. An autonomous agent wouldn't even need a pre-programmed digital twin of a factory floor to practice its navigation algorithms.
Exactly. Think about it. A robot could just roll into a warehouse, take a panoramic photograph of the shelving units, the machinery, and the obstacles, and its onboard VLM could instantly write the Python code to generate a perfect, physics-accurate 3D simulation of that exact room.
The robot then runs millions of training iterations inside a customized, natively generated simulation of its immediate reality.
Entirely bypassing human intervention. We aren't just teaching AI to parse the visual world anymore. We are giving it the framework to write the source code of reality, test its assumptions, and perfectly reconstruct its environment, one parameter at a time. Something to definitely think about.